All right, good afternoon, everyone, or good whatever time of the day it is when you're watching this video. This video is going to go over the answers to FRQ question number 7. This one is a bit of a curveball because it's not very quantitative, it's purely argument-based. This is one of the paragraph length response type questions. And it deals with concepts of what constitutes a system, whether a system is open or closed, and how we account for mechanical energy within a system. All right, so the first part, A, has two questions in it. The first says determine whether the system containing only the object is open or closed with regards to the mechanical energy of the system and state your reasoning. All right, so for this part, we're saying that our system is just the object here. So if we're trying to figure out whether the system is open or closed, first of all, we need to know what an open or closed system means. And what that means is for a system to be open, that means that energy can flow into or out of a system, which means that the total mechanical energy of the system is not conserved. All right, and that's because some external force is adding or removing energy from the system. All right, so the question really becomes, are there any external forces acting on this system? And there is an external force acting on this system, on this object. There's going to be a gravitational force, mg, pulling it down. So this force is going to cause the mechanical energy, specifically the kinetic energy of the object, to increase as it falls. So the answer to the first part is that the system is open, and that is because there's an external force that is doing work on the system. So the amount of work done by gravity is going to be exactly equal to the increase in the energy of the system, by the way. All right, so for part 2, now we're going to consider a second system that includes the object and the Earth. And the question is, now, is this system open or closed with respect to mechanical energy? So now, this gravitational force still exists within the system, but there's actually a pair of forces now. So just as the Earth pulls down on the object is going to pull up on the Earth with an equal and opposite force, so you call it Fg in both cases. All right, so these forces are equal and opposite per Newton's third law, so they end up canceling each other out, and in this case, these forces cannot be considered external, and there are no other forces acting on either of these objects, so there's no energy flowing in or out. That means the energy of the system is conserved. So all of these things mean that this system is closed. So in your answer, of course, you should put these bullet points into sentence form, but that's the basic argument here. All right, so maybe we should say one more thing about this. So the mechanical energy of the system can change only if there is some external force doing work on the system. In the first case, we had a system which was just the object. Gravity did work on the system, so the mechanical energy, meaning the kinetic energy of the object, changed as a result. It went up. For the second system, there are no external forces, meaning there's no work being done, which means that the energy of the system does not change. However, it's still true that the kinetic energy of the object is going to increase as it falls. So how do we account for this new way of thinking about the system? If you think about this in terms of bar charts, there's some initial kinetic energy of the system before the object falls, which will be 0. After the object falls, there is some amount of kinetic energy. And how do we make sure that the total energy of the system is balanced? Well, there's one other type of energy that exists when the system includes the Earth, and that is gravitational potential energy, which we'll call U. So that is actually going to decrease. So when the object and the Earth are far away, there's a lot of gravitational potential energy, and then as they move closer to each other, that decreases. And it turns out the decrease in the gravitational potential energy is going to exactly equal the increase in kinetic energy. So the total amount of energy in our system stays conserved. If we wanted to know how this bar chart will look different in the first case, where there is no gravitational potential energy, the difference there is that now we have something called work, which is adding some amount of energy to the system, and that becomes the kinetic energy. So we're just sort of labeling the energy in these systems a little bit differently. In one case, there's energy that actually flows from the environment into the system. In the second case, we just expand our system to include that environment, the Earth, so now we just have energy being transformed within the system. The physics is still the same, it's just a difference in how we choose to label things. All right, so we have one more question here. Part B says to determine whether the total momentum of the object Earth system increases, decreases, or stays the same as the object falls towards Earth. And then determine whether the kinetic energy of the object increases, decreases, or stays the same as the object falls towards Earth. All right, so we have two separate questions here. The first question concerns the total momentum of the object Earth system. All right, so as the object falls, it is going to gain momentum in the downward direction. We could call that negative momentum if we wanted to define a sign convention that way. So let's draw a before and after picture here, just to be really clear. So here's our object, and here's the Earth down below. To start, the initial momentum of the object is 0. The initial momentum of the Earth is also 0. As the object starts to fall, it starts moving this way. So now it is going to have momentum which is non-zero. Let's call this P final. Let's call this negative momentum to be really clear here. So what about the Earth? The Earth just stays at rest, right? Well, technically, there is a force acting on Earth. There's an upward gravitational force, which I drew up here. That force is going to act for a certain amount of time. So if you remember when we did Unit 5, we talked about this concept called impulse. The impulse is equal to the force that acts on an object multiplied by the time that it acts, and impulse equates to a change in momentum. So these two objects have equal and opposite forces acting on them, and they act for the same time. So there are going to be equal and opposite impulses delivered to these two objects. So believe it or not, the Earth in this frame would actually gain some positive momentum. Now, this would be utterly undetectable because the velocity of the Earth would be essentially 0 to many, many decimal places, but it would be just enough to give it momentum due to its large mass that matches that of the object. So the total momentum is still going to be 0. We have no external forces, therefore there's no change in momentum. All right, I haven't really left myself much room here, so I don't know if I can squeeze in the last part, but the last question, sorry about that. All right, I think it's done. Sorry about that. I'm not going to re-record this entire video, so sorry, we'll just have to deal with that. So the last question asks about kinetic energy of just the object as it falls toward the Earth. The question is whether that increases, decreases, or stays the same. And since the object starts at rest and it ends with some velocity, the kinetic energy of the object will increase. So the kinetic energy on its own does not have to be conserved, it's just the total energy that has to be conserved. And the kinetic energy is able to increase because the potential energy, gravitational potential energy to be more exact, will decrease. All right, so the total amount of energy is still conserved in this system if we consider both the object and the Earth, and the momentum is also conserved. And both of those facts stem from the fact that there are no external forces acting on the object. All right, so this was a bit of a different problem, but hopefully this explanation made sense. If you have any more questions, please feel free to contact me and let me know. All right, thank you for watching.